Hello, everyone. Welcome to the Reinforcement Learning Reading Club. In this session, we will be reading a paper from NeurIPS 2021, and Mohammadreza Nakhaei, a new PhD student in the Aalto Robot Learning Lab, will be presenting the paper. Mohammed, you can begin.
Okay, hello everyone. Thanks for listening to my talk on this paper. Let's jump in. Okay, we will have first an introduction, what is the motivation behind this paper. Then I will explain some background information such as the transformers and the GPT architecture. Then we will discuss the method used in this paper. Next comes my favorite part, the results and the discussion, and finally we will have a conclusion of this paper. Here comes the introduction part. Okay, what is the motivation behind this paper? As you know, we can see reinforcement learning as a sequence of decisions. In each time step, the agent observes some states, take an action, and a reward function is computed. So reinforcement learning is a sequence by nature. The idea is that we can train transformers on collected trajectories similar to supervised learning. In this paper, the authors use their method on offline reinforcement learning and on data sets. This method has some advantages, such as there is no bootstrapping, so the propagations of returns are really faster, no need for discount factor, so the undesired short-side behavior caused by discount factor can be avoided. And because of the self-attention mechanism, credit assignment the agent can assign critics directly, and so it may perform better. Here's an illustrative example. There's a graph, and the goal is to reach the goal state from the beginning. If the agent reach the goal state, then the reward is 0. On other states, the reward is -1. They're trained transformers conditioned on return state and action, and they trained that on random policy data. The interesting part was that the transformers could learn the optimal policy. So motivated by these illustrative examples, the authors used transformers in offline reinforcement learning. Here comes the background part. As you may know, transformers are originally used for sequence-to-sequence applications in natural language processing. So applications such as machine translation, sentence automations, and those fields. In comparison with recurrent neural networks such as LSTM, GRU, and other architectures, they usually have better performance, and they are able to learn longer patterns in the data. Since they're using positional encoding, they are trained faster on GPUs because the whole sequence can be fed into the architecture at once. Unlike the recurrent neural networks that at each time steps, the data should be fed to the network, and then the hidden state is computed for the next time step. As you can see here in the architecture, the basic transformers contain two parts. The first part is the encoder, and the second part is the decoder. Instead of here, the positional encoding, instead of the hidden state, you use positional encoding. So each sequence, each time step, for example, in reinforcement learning, each sequence is transformed into an embedding space, and then it is added to the input embedding. We have some residual connection with multi-attention mechanism in the encoder and decoder. And finally, the decoder takes the input from the output sequence and the output of the encoder and returns the output probability of the sequence. Here you can see the GPT, the original GPT architecture. This architecture consists of only a decoder. The main idea behind this architecture was to use unsupervised pre-training, then use supervised fine-tuning for a specific task. Originally, it was used for NLP tasks such as question answering, sentence similarity, and classifications. Uh, as you can see, the original architecture contains of 12 blocks, but in the paper, the authors made some modifications. The first one is that instead of text and position embeddings, we do not need text embedding because in reinforcement learning, we are dealing with numerical states and actions and rewards. So there is no need to text embedding. And secondly, instead of text prediction and text classifier, these modules are deleted and the next action is predicted. Finally, instead of the 12 blocks, they use the number of blocks as a hyperparameter for different environment. In some environment it was 3 and for some other it was 4. So the model has less parameters and it is trained faster. Up to here, if there's any question, I can answer. Okay, let's continue. So here is the architecture and here is the method used for training. Here you can see the pseudocode. There's a tuple of states, actions, and returns to go. At first, states, actions, and returns to go are transformed to the embedding space with a linear transformer, a linear layer in neural network. Then we have a positional encoding. Then states, actions, and reward embedding are added to the positional encoding and they are stacked together in the input embedding. The input embedding is fed to the transformer and the hidden states are computed. Based on the hidden states, the actions, the sequence of actions are predicted. This is the main model for the training.
Sorry,
Yes.
question. So, do all these embeddings have the same length?
Yes. We have the fixed length of K. Thanks for recalling that. We have the same length of K and the hidden state has the same dimensions. For example, the state, action, and returns to go are transformed linearly to an embedding with, for example, 128 dimensions.
Okay.
Then, yes. Is there any question?
No, you can continue.
Okay. So to review briefly, the transformers takes the returns to go states and actions up to this time step as input and output the next actions, actually a sequence of actions. Here comes the training loop into the data sets. It's really simple. The action is predicted based on the sequence of returns to go states and actions, and it is compared to the actions in the data sets, and a simple supervised learning is used. For the evaluation of the performance of this decision transformer, we have a target return. For example, here is one, but it's based for every environment, it can be different. It's actually the return we want to reach at the end of the episode. So at first, there are some sequence of return to go states, which is the initial states, actions, which is empty, and the time steps. While the episode is not finished, based on the previous sequence, an action is determined and the action is taken in the environment, then here comes the important part. The return to goal is computed by subtracting this time step reward so that in the next time step the return to goal is computed. And then states and actions and time step is appended to the sequence, and this procedure is continued until the episode is finished and we see the final return. As you can see, the trajectory here is consists of return to go, states, and actions. Here comes the interesting part, which is
Sorry.
yes.
Yeah. So here the target return, it means the reward for one step, right?
The target returns means the return we want to reach. For example, in a cartable environment, a simple environment, the maximum reward, the maximum possible return is 500, I think. So the initial target return is 500. But at each time step, we have a reward of 1 if the agent hasn't failed. So at each time step, the return to go, target return or return to go is computed by subtracting the reward and the target return. For example, in the second time step, the return to becomes 499 in cartable example. Could I explain it?
Yeah. Okay, please continue.
Okay. So here comes the results. The first one is the results of Atari Games, and the author used 1% of all samples in DQ and replay datasets. The original dataset consists of 5 million samples. So here they use 1% of that. For scores, they normal the score such that 100 means a professional gamer score and 0 represents a random policy. As you can see in um, Atari Games, decision transformer was able in some environment to learn the task better than other algorithms such as conservative Q-learning, QRDQN, behavior cloning, and REM. These are strong algorithms in offline reinforcement learning, but in QBERT and Pong, the conservative Q-learning performed better. In QBERT, we can say that the decision transformer didn't have a good performance compared to other algorithms, but in other it was acceptable and even can outperform the other methods. For the OpenAI gym environment, they use the D4RL benchmark and they created a 2D richer environment. They used 3 different datasets. The first one is called medium, which consists of 1,000,000 time steps generated by a medium policy, which means that it could score roughly around 1/3 of the highest value. The second dataset is a medium replay, which is the agent is trained on a performance of, again, the median policy, but instead of 1,000,000 time steps, we have something around 25,000 up to 400,000 time steps. I think 25,000 in OpenAI gym environment and 400,000 in the richer environment they created. And finally, the final dataset is medium expert, which consists of 2 million time steps And the first 1 million is similar to the first data set, and the second one is the samples generated by an expert policy. So we have 3 different data sets. As you can see here, this is compared to some other algorithms such as conservative Q learning, pair, and behavior cloning. I'm only familiar with these 3 algorithms. So as you can see, when we have a medium expert data sets, there are better samples. So the score, the returns of the results should be higher compared to other data sets, and it's rational. If we want to compare the results of decision transformers to other algorithms, we can see that in most cases it outperforms the other algorithms, especially when especially not in the case of medium and medium replay data sets. And in other environments, the performance is acceptable. For example, in medium expert data set in the Hopper environment, the best performance is for conservative Q learning, which is 111, and the decision transformer is 107 roughly. So it's acceptable. On average, the decision transformer has better performance compared to other algorithms. Here is the distribution of returns. It means that, okay, if I change the value of the desired return, the return to go, I expect the actual return, the obtained returns to match that, or if it doesn't match, it has a high correlation with the target return. As you can see, this is the case for many of the environments. For example, in the breakout, if we increase the desired return, then the obtained return is also increased, and there is a good correlation here. The yellow line indicates the best trajectory in the data sets. And as you can see in many environments, for example, in Sequest and in the, for example, QBERT, the decision transformer was able to reach the performance better than the best trajectory in the data sets. But in other environment, for example, in the worst case is in the I think is in this case in the Walker environment, when we have a trajectory with the performance of roughly 110 return, but the performance of decision transformers cannot go beyond something like 95, 90, I think. But overall, there's a correlation between the target return and the return the agents can obtain. Here is the question of long-term credit assignment. So they use a different environment, which is a key tutor environment. This environment contains of 3 phases. The first one, the agent is in a room, and in the room, there is a key in the room. In the second phase, the agent is in another room, and it's just for distraction. And finally comes the final room, which there is a door at this room, but the agent must have picked up the key in the first room so that it could win and unlock the door. For this purpose, they use the entire episode length. Percentile VC means the behavior cloning algorithm only on successful trajectories. So in the data sets, there is a data set, and a random policy only is successful roughly around 3% of times. As you can see, after the training on 100 random trajectories, the decision transformer was able to uh, successfully unlock the door in roughly 72% of the time, while other algorithms failed to be successful. When we increase the number of trajectories, then the number of successful trajectories also increase. And if we train behavior cloning only on successful trajectories, then it has a better performance. But as you can see, again, the decision transformer has a acceptable performance. In roughly 94.6% of the time, it is successful. The interesting part in this environment is that it needs to uh, assign credit in the first stage of the training, in the first stage of the episodes. So it's really a long-term credit assignment. And as you can see, decision transformer, even if they are trained on random policies, they are able to learn meaningful, they are able to learn meaningful behavior. The next question comes is in the second question. The next question actually is that if we can use decision transformers in a sparse reward environment, and and another question is that we can use that as a critic. Um, if we can use them as a critic in a sparse reward environment. So up to here, we only use transformers to predict the next actions. But now there's some modifications so that it could output the returns. As you can see here, the probability of being successful for different scenarios. If the agent did not pick up the key, so the probability of being successful is around 20%. But if the agent pick up the key in the second phase, and, and the probability is around 40 to 50%. And in the final phase, if it's able to reach the door, the probability of being successful converge to 100%, and otherwise it's converge to 0. As you can see from this figure and this plot, we can understand that decision transformers can be used as a critic in reinforcement learning. And in the case of a sparse reward, when the agent receives the total reward in the final time steps, while other algorithms are affected by this change, decision transformers are not really affected. For example, in the original dense environment, the performance of decision transformers is 107, and in the sparse settings is 103. There is only 0.3 reduction in the performance. This is the same for other data sets in the Hopper environment, but for the conservative Q learning, as you can see, it's from 111, the performance is reduced to 9 in the medium expert environment. And in the behavior cloning, again, if we only train the behavior cloning on successful data, on some cases, for example, only in the medium data sets, it can outperform the decision transformer. But in other cases, even if even that the behavior cloning is only trained on successful trajectories, but the performance of decision transformer is better, and it means that decision transformer can actually extrapolate to the data sets. Here comes the final part, which is the conclusion. So briefly, the decision transformers can match and even outperform a strong algorithm in offline reinforcement learning with minimal modification from standard language modeling architectures. There are some ideas. The first one is that they could change the embedding of return state and actions. So maybe more complex embedding might be more useful. This work was done in offline reinforcement learning. Upside down reinforcement learning is an algorithm that tries to solve our problems using supervised learning techniques, and it's really similar to this work. We can transformers, for example, GPT model can also be used in the behavior function of upside down reinforcement learning for online RL problems. And I did some experiment with this, and actually the GPT architecture can improve the performance compared to fully connected neural networks in upside down RL. Thank you for your attention, and if there's any questions, I'm available.
Thanks, Mohammadreza, for the interesting talk. Are there any questions? So I can ask one question.
Sure.
So if I understood this correctly, it could be more this paper at least could be more seen as a supervised learning
Yes,
paper, right?
exactly.
So
Yes.
so
Because
how yeah.
because we have a data set from, for example, DQ agents, and it is actually using a simple supervised learning on a sequence-to-sequence model. This paper actually see the offline reinforcement learning as a sequence-to-sequence problem and train a simple transformer here, a GPT model, on these data sets.
Yeah, and I'm curious to know how it could be applied to online RL settings.
Okay, and in here, as I said, there's an algorithm called upside down reinforcement learning. In upside down reinforcement learning, similar to here we have a desired target, we have a desired return, the target return. In that setting, we have desired return and desired, I think, horizon, the number of time steps. And the difference between upside down reinforcement learning is that at each iteration, it is trained on some data, some samples from a replay buffer, and then there's some new trajectories are generated based on a new command. So here
Yes.
we, at each iteration, we train the decision transformer, and then based on and we hope that, okay, the performance has improved, so we must create new trajectories, we must generate new trajectories that are better than the old one. So it becomes online reinforcement learning.
Yeah, so I guess in that case, the challenge would be that the distribution of the training data is changing during the training.
Yes.
Yeah.
Okay, but also the distribution of the training is changing, the distribution of data is changing. In upside down reinforcement learning, there is a fixed size replay buffer, and it only store the trajectories with highest returns. So they bias the learnings toward the better performance.
Yeah, thanks. Any other questions from the audience? Okay, so if there's not any questions, I should thank you again, Mohammadreza, and thanks everyone for joining us here, and have a nice weekend to you all. Thank you, Mohammed.
And thanks. Thanks for having me.
Thank
Bye.
you. Bye.
Bye, everyone.